All right, moving on to lesson 12.2. We're going to focus on rational functions now. So, yep, that's going to be our first word in the vocab. A rational function, don't mind my sloppy writing, is a function whose rule is a quotient of polynomials. So that just means what the rule, like what it is a quotient, so a fraction division of polynomials in which the denominator has a degree of at least 1. So in other words, you can think about it being there must be a variable in the denominator. We focused on inverse variations in 12.1. That is a type of rational function. So now we're expanding what we know, and we're going to learn about all the rational, or more, in general, more rational functions, and we saw one specific type. So some examples here, we can see y equals 2 divided by x. So that's an inverse variation, k, a constant, divided by just the x. So that's an inverse variation, but the bigger umbrella is that it's a rational function. So the next one, y equals 3 divided by 4 minus 2x. This has a degree of 1, x to the first power, but you can see this looks different than 2 over x, the more basic inverse variation. This is a rational function. Y equals 1 over x squared. We might have some higher exponents in our denominator as long as the degree that it's an x to the first power or higher. Those are all rational functions. All right, so because we are talking about rational functions, which is division of polynomials, which will have a variable in the denominator, that means we have to think about what we're dividing by. This idea of excluded values is very important. So an excluded value is any x value that makes the function value y undefined. So if you think about when you're dividing polynomials, you just have to make sure that you're never dividing by 0. And so what x value would make the denominator equal to 0, and that will be a value we have to exclude for our functions. It'll be part of our domain. X just can't be this number. So for a rational function, an excluded value is any value that makes the denominator equal to 0. So we're going to be asked to identify excluded values. Here we have two rational functions. What you want to remember is that it all comes down to the denominator, so we have to make sure that our denominator doesn't equal 0. So the easiest thing to do is let's just circle that denominator, and whatever it is, we have to make sure that it does not equal 0. Okay? So now let's take a look. We have x. If there's any solving to do right here, we would solve that. And when I put this does not equal to, that's indicating we have to exclude or let x not equal this value. So x does not equal 0. 0 is the excluded value. So let's think about it. If you were to plug a 0 in for x, what's 8 divided by 0? Maybe I'll write that down as we talk through it. Oops. And then even if you're not sure, type 8 divided by 0 into your calculator and you get a domain error message because you can't divide by 0 in math. So we can't let that happen, so our excluded value is 0. You can write that as x cannot equal or does not equal 0, or you could say excluded value is 0. Those two statements are saying the same thing. All right, so we have another rational function, y equals 3 divided by x plus 3. Identify the excluded value. So again, we focus on the denominator. Honestly, it doesn't even matter what the numerator is. Excluded values is all about the denominator because division, what you're dividing by, that's where we have issues in math. We have to make sure we never divide by 0. So you take your excluded value, x plus 3, And this is our denominator right here. So whatever your denominator is, it just cannot equal 0. Because this is not just x alone right here, it's x plus 3 cannot equal 0. Just treat it like an equation. Let's go ahead and solve for x. So we'll subtract 3 from both sides. So x does not equal or cannot equal a negative 3. That is our excluded value. We also could write it out. Excluded value is negative 3. So 2 ways to say that. And let's just make sure we understand why. If I were to take the original function, y equals 3 over, and we're saying that x can't be a negative 3. So what happens if we plug in a negative 3 for x? Negative 3 plus 3, so y equals 3 divided by negative 3 plus 3 is 0. Oh, we can't divide by 0, so we have to make sure that x is never that value. Okay, so a little more vocab to go over. Most rational functions are discontinuous functions. So discontinuous functions, meaning their graphs contain one or more jumps, breaks, or holes. This will occur at an excluded value. So those excluded values we just talked about will have a break in the graph, or a jump, or a hole, or something like that. One place that a graph of a rational function is discontinuous is at an asymptote. So this is we got a lot of good vocab in chapter 12 for you guys. An asymptote is a line that a graph gets closer to but never crosses. So if you look at this example right here, this graph, in the graph shown, the x and y axes are asymptotes. This is what we were graphing in 12.1. Here's our inverse variation, y equals k over x, 1 over x. Remember how we drew those lines and we just never touched the x and y axis? That's because we have a horizontal asymptote right here, and we have a vertical asymptote right here. Maybe pink wasn't the best color. And you can tell that our curves will never touch those asymptotes. For rational functions, asymptotes will occur at the excluded values, which we said above, but now we're going to say it again. All right, so we are going to identify horizontal and vertical asymptotes. So I have some notes you guys have to write in that are not typed in. So a vertical, oops, come on, there we go, asymptote is when the denominator is equal to 0. Basically that excluded value that we found. That's going to give us a vertical asymptote. The horizontal asymptote is the constant value. Ooh. This gets so sloppy sometimes. All right. At the end, and I'll show you what I mean by that. Okay, so get those written in your notes, and then let's actually find the asymptotes. For this first example, y equals 1 divided by x minus 6. So I'm going to do some writing up here. The horizontal asymptote, take your denominator, x minus 6, set it equal to 0. Oh, I did not mean to say horizontal. I meant to say vertical. So we'll just make that a vertical asymptote. You take your denominator and set it equal to 0. And then look what I did right here. I'm just so used to saying not equal to. All right, we'll get it together. Here we go. All right, so we took our denominator, x minus 6, and we set it equal to 0, and then we're just going to solve. So x equals positive 6 is an equation of a vertical line. Remember, our horizontal and vertical lines are super basic like that. And you have the x equal to a number for your vertical asymptote. All right, your horizontal asymptote is going to be the constant value at the end. So our second example is very clear. You can see here's the constant value at the end, that minus 7. Okay? If you have a function, a rational function that does not have that, I should use a different color, like ours, you can add in a plus 0. And then our horizontal asymptote will be a horizontal line, so y equals, and then whatever that value is, 0. Okay. Let's keep working on this. So here's our second rational function. We're going to find the vertical asymptote first. Vertical asymptote is set your denominator equal to 0. So 3x minus 10 equals 0. Solve for x. We're going to add 10 to both sides. 3x equals 10. Divide by 3. X equals 10/3. It's okay if it's a fraction. Not all vertical lines hit at exact points, but that's your vertical asymptote. Our horizontal asymptote is that constant value on the end. So if I look at the function, I can see there's a minus 7. So it has to be y equals. You have to include the x equals or y equals, and then we're going to say negative 7. All right, you guys, thanks for hanging in there. I know this is a long intro video, but there's just a lot of content in this lesson, and we're hitting on the ideas, and then we'll go and review them all in the example videos. Anyway, all right, so graphing irrational functions using our asymptotes. We actually really like the asymptotes. They help us with our graphing. So step 1, identify vertical and horizontal asymptotes. So vertical asymptotes is we set your denominator, x minus 2 equal to 0, and solve. Add 2 to both sides. X equals 2 is our vertical asymptote. Horizontal asymptote is we look for the constant on the end, minus 4, so we have to put it in the form y equals, a little neater looking than that, y equals negative 4. All right, so that's our first step, is we want to identify any horizontal and vertical asymptotes. Okay, now we graph the asymptotes using dashed lines. So I have x equals 2, so I'm going to go to the graph. This is a vertical asymptote. It says x equals 2, so I'm going to plot the point at 2, and I'm going to draw a vertical line. Dashed lines. The reason why we're doing dash is technically this is not part of our graph of our rational function, but it certainly is our guide. We know that we're never going to touch that line with the curves that we're drawing. So our asymptotes give us good guides when we're graphing. The horizontal is y equals negative 4, so I'm going to go to the y-axis at negative 4. It's a horizontal asymptote, so we're going to draw a horizontal line. And honestly, what it kind of is like is when we had our inverse variations and we had curves that kind of were in between the axes like that, it's almost like we've just shifted our axis over to here. We won't use this as the new origin, but now our curve will either be here and here, or it could be here and here. Okay, so step 1, we graphed our asymptotes from the dashed lines. Step 2, make a table of values. Choose x values on both sides of the vertical asymptote. So I'm going to just rewrite our function so we can see it over here. Y equals 1 over x minus 2, and then minus 4. Okay, so, you know, we may not get some pretty numbers on this, but we'll just plug in numbers and plot. If we get some fractions or decimals, that's okay. As long as we're getting just accurate values on our curves, we'll be able to draw the curves. So it says make a table of values, choose x values on both sides of the vertical asymptote. So remember, our vertical asymptote was x equals 2. Okay, so think about a table of values with 4 values. Here's our cutoff, or not our cutoff, that's our middle guy, x equals 2. So I need a number, 2 numbers on the right of 2 and 2 numbers on the left of 2. So I don't know, let's see, what could we plug in? Anything bigger than 2. My graph goes up to 9, so I could plug in, let's say, a 4, and maybe a 6. Then I need 2 values that are going to be on the left side or less than 2, so maybe a 0 and a -2. Again, what you choose doesn't matter as long as it's 2 points on the right and 2 points on the left of your vertical asymptote. So now we're just going to do the math. We're going to plug these numbers in, calculate the y values, and plot those points. So y equals, let's see, we have 1 over, I'm going to start with that, -2 minus 2 minus 4. -2 minus 2 is a -4 minus 4. Here's where your calculators with a fraction button will come in handy. You can just type in a -1/4, subtract 4, and see what you get. This will be a -4 1/4, or maybe a -4.25 if that's easier to think about graphing. And then we're just going to plug this in for the 0 now. Y equals 1 over 0 minus 2 minus 4. 0 minus 2 is a -2. And -1/2 minus 4 is -4.5, so -4.5. Now we're going to do the same thing with the 4 and the 6. So y equals 1 over, I'm plugging in a 4 for x, 4 minus 2 minus 4. 4 minus 2 is 1/2 minus 4, and 1/2 minus 4 is -3.5, or -3.5. And then lastly, plug in a 6. Let's see, I'll do it over here. Y equals 1 over 6 minus 2 minus 4 on the end. 1 over 6 minus 2 is 1/4 minus 4, which is a -3 3/4. Or we could say a -3.75. Okay, I feel like maybe I should have picked some x values that were more spaced apart, but that's okay. As long as we can plot these points and see where the curve is going to land, then we're good. Okay, so let's plot these. We have a -2, -4.25. Oh, that's really close to the asymptote right there. I'm going to estimate right there. 0 and -4.5 is going to be right there. So it's kind of hard to tell, but at least I know the curve is over here. That's kind of what that's helping me with. And it gets right close up to the asymptotes. All right, 4 and -3.75 is going to be about there. And 6 and -3.75 is even closer to the asymptote. So again, we know that our curve is going to be over here. Okay, so again, use your calculators when you guys are doing this table of values. I don't want you to spend a ton of time getting those points, because once we plot them, it's honestly just showing us where our curves will be. They are important values, but I don't want you to get bogged down in the calculations.